Yes, thank you very much, Paul, for the introduction. First and foremost, I would like to say I'm always, but often the guy who stands up presenting this project, but want to make clear that this is really a team effort. Many people, colleagues, partners work on this, so I will use also this opportunity to shamelessly advertise their talks and posters later on in the ETC conference. So, already my apologies for that. You all know why we are here for the Anibal Energy Storage, so I'm not going to dive into why we need it. I'm going to go straight into the project. So to give you a little bit of context, currently we have this nice old coal-fired plant in Delft, now gas-fired, that's fueling our local district heating network that we have in Delft, and we present 100% of our emissions that we now have for these old faculty buildings. As Paul said, we have drilled this geothermal well 2 years ago, and we're now finalizing this surface plans here, so you see the temperature levels, so we need a heat pump to boost temperature levels, but we have enough heat to also deliver to the city, so that's the pipe connection under the river that Paul mentioned, and so we supply the old faculty buildings of the TU Delft together with the city. But there's a challenge here. You see the demand profile and the power that the geothermal well will supply constantly throughout the year, so there's a clear mismatch. We cannot meet peak demands, mid-loads, peak loads in the winter months, and we have some excess in summer. So that's where this drop in the emissions come from. And so from 100% we only reduce 60% because of this. And so we can supply a decent amount, but far from everything. So that's where the high temperature UTES comes in. And so this excess that we have here, we now store locally at 200 meters deep aquifer that allows us to in winter additionally supply the heat, and then we really get too close to 100% renewable energy together with geothermal and the high temperature UTES. We talked a bit already about sector coupling earlier today, so we have this heat pump center with a big heat pump anyways for the winter supply of heat that is idle in summer, so when we have cheap electricity prices, that offers the opportunity to additionally charge the UTES system in summer. And this is part of a bigger European project called Push It, that we also do a lot of research alongside this high temperature UTES system. And if you want to know more details, I will post on this on Thursday as well. And now some of the innovation highlights that we have in the project here relate to impact and performance. So we have higher temperatures to store, up to 90 degrees, while the ambient conditions in the local aquifer is around 13. So we get this buoyancy flow, because you're probably all familiar with. We are targeting a very heterogeneous formation, so we need to know the aquifer characterization together with the heat distribution to assess where the heat will move to in this dense urban area, or also maybe other users use the subsurface, and also manage that our losses so that our recovery is as high as we like it to be. So characterization is quite an important element here. So we took several cores, so this is the storage aquifer, 120 to 180 meters deep, that's where we target. We took several cores. This is from an offset well in the well on campus. We took some more cores. We are testing those cores in the lab on high performance at the full meter scale, but also at smaller plug scales. That's the heat capacity and conductivity characteristics. So all about this, and so there are several posters and talks on this characterization, also the larger scale characterization that we have, the chemical microbiological characterization. Many things are going on here, so if you're interested, better please go to their talks and poster sessions. Also, we quite intensely going to measure the temperature plume, and so we have the 3 lukewarm wells and the 2 hot wells, and then zoomed in here. So we're going to make a whole monitoring array around these wells to measure the temperature level, the temperature plume across the whole vertical interface. So these diamonds there are UTES monitoring boreholes. Here it's still working more. Monitoring boreholes, so a whole array. We're going to have several observation wells to also measure the water quality changes in the aquifer itself as well. So also the temperature losses along the well casing are important here. That's work that's done by Delft. And we assign here designed this temperature network of DTS monitoring points. So please go visit them as well to get more details on this. Then the wells, and we did quite some extensive work on different completions for the wells, different types of grouting materials as well as casing materials as well. So that's novel. Also, we're looking at different novel types of drilling methods, and we're not going to, due to the research that we did, we're not going to take this approach, but we did come to some fundamental insights on stability of such larger diameter wells. So also here we have a poster session really focusing on completions materials like Alexis here on tomorrow. And then I want to talk, I was quite good now, I want to talk a bit more in detail because Paul also asked me to say something about the business case of these types of systems. So, and that all boils down a bit to this system integration and control. Here on the left you see again my very basic schematic, and this little arrow here, if you ask a consultancy engineering company to make a P&ID for it, this is what you get back. You see quite some of these arrows, and these are not even all the arrows with all the energy flows, so you already quite quickly see that in all these large-scale heat storage projects, this is becoming a mess. And we also transporting heat across very large distances, so as a result there's a lot of inertia, difficult to control, and how to operate the system is very, very challenging. And that's also where this business case issue comes in. So for this, so we developed this co-simulation framework, and that's not that novel in itself, but doing this for such a complex system is quite a feat to accomplish. So we have the subsurface model, simulation model together with the energy flows at surface, all the installations that we have, we could model this in conjunction with each other. And then you see a bit how you actually are able to operate and get the system to work. Here you see we schematize in the simulation the energy demand according to a sine function. So to keep it a bit simpler, and first you need to charge a lot because you're charging against the ambient temperature, so that is not great. And we have also a pump here. But here you see in the 10th year that you are actually, you lose some of the heat in the UTES system, and so this is actually losses, but you see that the yellow part, where you actually use the UTES, grows to quite substantial parts in the coming years. But to the extent at which this occurs matters a lot to the assumptions that you have here in the surface pump. What temperature levels do you have? What mode operation and switching between different systems. Right. What is on the last slides? I had some points there on the business case. Key thing here is on the business case is that there's quite some what we now see in the business case where we compare the system as a whole with and without the high temperature UTES, that we see either a very small reduction in internal rate of return or a relatively reasonable improvement of rate of return. And why this is so close to zero has all to do with some conservatism. There's quite some conservatism in this design, that they make all kinds of things relatively robust in how they operate the system, conservative assumptions, and that caused that this UTES in their business model that is now being done by the company that operates the system, that's not as stable as you think it can be if you fully utilize. And of course, this is a novel technology they don't want to rely. So at this point, it is logic that this happens, but it makes it difficult to get to a financial investment decision. And then the last but not least innovation highlight relates to societal engagement. There's quite some things going on. If you have such a drilling rig in an urban environment, that's quite intrusive. There's quite some work going on this also. There's this roundtable discussion during session PC on Wednesday, which is interesting to go to if you're interested in these kinds of elements. Then, my last slide, status. The service plans are now being finalized. The UTES wells will be drilled early next year. So roughly, we start delivering heat from the system already in the coming winter, and then the UTES will be fired up in the next summer. Lessons so far. High temperature UTES really helps to increase renewability or renewable energy supply. But the key element here is that UTES is not just an add-on. So the technical, financial should also be here, and organizational integration is quite challenging, especially as this usually concerns large-scale systems. So there are many stakeholders there. So that's very difficult to optimally integrate. This relates to the conservatism. And so if you take it away, it does conservative and this gradual stabilization, and together with the dynamic temperature cutoffs and temperature set points really helps to increase the performance and really optimally utilize this technology. And we have already many novel insights into it, but the research is of course still ongoing. And with that, I would like to end my talk.